Everything's okay? Okay, good morning. Welcome to the third lecture for the back to experiments. Maybe, yeah. Okay, better? Yeah, okay, so sorry, what is it? Hello? Okay, so okay, so back to the world of experiments. After hearing Javier's lecture yesterday, I think it's actually very well timed now, so I can speak more understandably, hopefully, about Axion experiments in particular today. So I wanted to basically continue finishing up the second topic, which is ultralight dark matter, of which I'm grouping axions in the same category. And then for the second lecture this morning, we'll move to the last topic, which will be searching for new spin-dependent forces and how that relates to how those relate to the experiments I'll talk about in the first lecture. Okay, so last time we saw this table from this nice paper from a few years ago where sort of a nice listing was made depending on the type of coupling for different kinds of ultralight dark matter. We talked last time exclusively about the scalar dark matter, and for this lecture I'm going to move to the next column here, or the next row rather, where we'll talk about axion dark matter in particular, and the three different ways it can couple in experiments, so namely to the gluons, to the photons, or also to fermions. Okay, so we've already now at this meeting heard quite a bit of motivation for axions, how they're quite generic from a theoretical point of view, and how you should expect to find them in a lot of theories beyond the standard model. And of course, the favorite axion is the one that can also solve the strong CP problem. And we've already heard nice lectures on why the axion is a very reasonable choice for a dark matter candidate. So the axion can couple to matter in basically three ways that result in signals in experiments, at least for axion dark matter. So we have the first term here is the Primakov effect, where axions are coupling to photons. And there are some experiments I'm going to talk about, some of which were already mentioned yesterday, that are searching for the axion, relying on measuring this coupling. So the ADMX experiment is the only experiment that's actively running right now that's currently searching for axions. And then there's some other experiments, for example, dark matter radio and LC circuit-based experiments that are being developed at the moment to also look along this avenue. And so here, this is coupling to the electromagnetic field. Of course, the axion was invented to couple to the gluon field in order to explain the strong CP problem. And there are experiments that are being currently developed to search for this coupling. Generically, one might also expect the axion to couple to fermions through this derivative type coupling. And there are experiments as well looking in this direction. So as far as the gluon field, the Casper experiment, Casper electric as it's called, and I'll explain why that's a reasonable name for it shortly, is looking for this coupling to the gluon. And then as far as fermions, we have a different variant of this Casper experiment called Casper Wind. Both of these experiments rely on the axion coupling to nucleons as opposed to the experiments up here, which are looking for axions coupling to photons. And then there's also another experiment that's actually quite close to where we are here in Padova, the QAX, or Quest for the Axion experiment that's being developed that's looking for coupling of axions to electrons. I'll say a little bit about each of these experiments in this lecture. Okay, so as we heard yesterday, at least for the QCD axion, there's a well-defined relation between the mass of the axion and this Petrie-Quinn symmetry breaking scale F axion, where this numerator here is basically lambda QCD squared. And so for generic axion-like particles, however, I just wanted to re-emphasize that this relation is not necessarily held. So axion-like particles could have different values, basically. So the mass and the F are not necessarily connected. Okay, so let's look at for the QCD axion in particular. So this is an adaptation of a plot that you've already seen in Javier's lectures yesterday. And so I'll just go over this a bit slowly so to cover everything. So what I have here on the x-axis here is the axion mass in EV from MeV all the way down to nano EV and below on the other scale. On the top axis here, you could also put the F axion as 1 over the mass. Since this is the QCD axion, there's a relation. But for simplicity, I just have the mass here, so we can just talk about one parameter. So let's start with the blue area. So the blue areas here are constraints on the axion mass from various astrophysical observations. So we have white dwarf limits, red giants, globular clusters, supernovas, 1987A, and also constraints from the CMB, BBN, and hot dark matter. So these constraints already were discussed in some detail by Javier yesterday, so I wasn't going to spend any time saying anything about the details of that, but you can see kind of the point that there's a lot of astrophysical evidence that suggests the axion mass has to be lower than sort of 10 milli-electron volts, because higher than that, up to this range, has pretty well been ruled out by astrophysical observations. The gray areas here, colored gray, are actual bounds from experiments. So the CAST experiment, the CERN Axion Solar Telescope, which I'll explain a little more about later, has an experimental bound over here. The ADMX experiment, looking for axions converting to photons in a cavity, has a pretty narrow slice here that they've ruled out in terms of where the axion mass could be. There's telescope results, beam dump results, and as well as some limits from the xenon experiment. So there's kind of a scattering of lab experiments that have placed constraints as well. There's some hints here from white dwarf cooling, for example, which suggests there may be something interesting going on kind of at the 10 milli-electron volt level. The green bars here are projections for proposed either improvements to existing experiments or new experiments. So the IAXO is basically a significantly built up version of the CAST experiment that would be able to experimentally check for solar axion conversion, that would be able to place bounds over quite a large range from 10 milli eV all the way up to over keV. The next generation of the ADMX experiment will be able to probe another order of magnitude or so towards heavier axion masses. The CASPER experiment, which I'll explain in the second half of the lecture, will be able to look for kind of nano EV axions and below. And then there'll be some other experiments I'll discuss that will fill in something in the space in between potentially. So there's also some constraints from cosmology. So that's the upper left corner here on the plot. So we heard yesterday there were two possible scenarios for cosmology that are relevant for the Axion. In particular, it depends on whether inflation happens before or after the PQ transition, right? So in the type 1 scenario, where we have early inflation, high energy scale inflation, that's the second bar here, where if the Axion is lighter than on the order of, say, 10 micro electron volts, then there'd be too much cold dark matter, and it would overclose the universe. However, in the type 2 scenario that we heard about, where the PQ transition happens before inflation, then we could be in some patch of the universe where locally inflation happened, and then we happened to live in a place where we had a small initial misalignment angle. In that case, there could still not be too much dark matter, even if the Axion was very light. And so in this type 2 scenario, then of course this whole area here would still be allowed. So looking a little more at these cosmological constraints, this is a plot from a paper in 2014 that came out shortly after this BICEP experiment claimed to possibly detect primordial gravitational waves, thereby signifying a very high energy scale of inflation. Of course, this experimental result was proven to be likely just a dust effect or a foreground effect, and so this went away. But nevertheless, this is a nice analysis that came out of that shortly after that result. So this is now a plot showing the energy scale of inflation in GeV from 10 to the 4 up to above 10 to the 14. And then this is the Axion decay constant from 10 to the 8 up to 10 to the 18 GeV. And so if BICEP had in fact detected primordial gravitational waves, that would have pinned down the energy scale of inflation to be a very high value above 10 to the 14 GeV in some narrow window over here. And so that would have constrained the Axion mass, which is on this axis, to be kind of in this milli-eV range and not below about tens of micro electron volts. Otherwise, you'd produce too much dark matter. So this part of the plot here corresponds to our scenario 1, basically, where we have a high energy scale of inflation. Then the Axion mass here could be bounded by a pretty narrow region around this kind of several milli-electron volts to several micro-electron volts. So there's bounds here from isocurvature fluctuations. There's a question after Javier's talk about isocurvature fluctuations from inflation. So that puts a pretty severe constraint on the mass of the Axion in this regime. And in this zone over here, you'd simply overclose the universe by having too much cold dark matter. Now in the scenario 2, where energy scale of inflation is very low, now here, depending on this initial misalignment angle, this is order 1 down to 10 minus 3, 10 minus 4, you see it's possible here to have a very high F Axion, in other words, a very light mass of the Axion, nano electron volts or even smaller. And so experimentally, we don't want to necessarily make a bias and assume that we're in scenario 1, but I think it's important to cover all the range of possibilities to search for the Axion mass over this entire range over which its mass may be. Okay, so in this lecture, I'm going to basically talk about some of the different experimental techniques and how they work and what the limitations are for looking for Axion dark matter. So the first, in black here, these are the experiments that are looking for Axion coupling to photons at various frequency ranges with various sensitivities, and I'll explain in detail kind of the differences between these and the merits of each approach. Then I want to say a little bit about Axion searches that are not, I would say these are not strictly Axion dark matter experiments, but they're Axion experiments nevertheless. So in particular, the CAST and the IAXO experiment are looking for the conversion of solar axions to photons in a magnetic field. And in this way, they're not so much dependent on cosmological assumptions, but rather on our knowledge of solar physics. And also the ALPS, the any light particle search 1 and 2. And so these experiments are, strictly speaking, not sensitive enough to look for the QCD axion, but they're quite useful for searching for axion-like particles. And they have the advantage that there's very little model dependence in the sense that these experiments are actually producing the axions locally in the lab. And so it's a nice way of checking for these production of these particles without any assumptions about solar physics or dark matter. And then at the last part of the lecture, I will talk about nuclear experiments looking for axions coupling nuclei and electrons. So these are the Casper electric and wind experiments, which are based on NMR, and then the QUAX experiment at the end, which is based on electron spin resonance. Okay, so the vast majority of the work in this field has been done on looking for the first type of coupling, the coupling of axions to photons. And this is a plot of the parameter space for limits on this parameter G alpha gamma gamma. So this is the Lagrangian now parameterized in the following way, where you just have the prefactor of A times E dot B as some coefficient that we call GA gamma gamma, and that's what's on this axis here on the plot. And then we have the axion mass here in EV on the bottom from 1 EV over here down to micro EV down here. So the Axion Dark Matter experiment has been, until very recently, the only experiment that's been able to probe into this predicted range for this coupling constant according to the KSVZ or DFSZ models of the axion. So the KSVZ model was explained by Javier nicely yesterday. And so this is a kind of a theoretically motivated coupling strength to search for, and is a good target for experiments to try to reach. And so ADMX has reached into this parameter space over a range of masses here in the kind of micro EV range, and in the future they hope to expand this onto something like where this dotted line is and cover an order of magnitude or more of the allowed parameter space there. The CAST experiment, the solar axion experiment, has a bound here in the shaded blue zone and is able to intersect with the QCD Axion line here for masses of order EV. The IAXO upgrade of that experiment would be able to get to this dotted line, which would then start to get into the axion parameter space more at below 100 milli electron volts. The Axion shining light through walls ALPS experiment has bounds up over here, and so forth. And so I'll just explain a bit about how these experiments work. So we'll start off with what we call Helioscopes. So the Helioscope was already introduced yesterday by Javier. Basically, it's a way of detecting the surrounding dark matter halo in our galaxy that would be present on the Earth, one would assume. And so we want to basically look for a cosmic axion that can come along and convert into a real photon inside the laboratory. And so this is the principle of the Helioscope, the ADMX experiment, which is currently running, as well as its high-frequency cousin, ADMX HF, which has been recently renamed to Haystack. So I haven't changed that in the slide yet. But and then there's an experiment in the Center for Axion and Precision Physics in Korea that's similar, as well as the Oregon experiment in Australia, all working on this basic principle. So you have a strong magnetic field in a cavity, and as Javier was explaining yesterday, an axion can come in and through this E dot B coupling in the background magnetic field of the cavity produce a real photon in the cavity, which looks like excess microwave power in the cavity. And so the idea is you have some tuning rod or something inside the cavity where you can scan the frequency of the cavity, and you look at the noise, basically. You look at the noise in the cavity and say, okay, is there excess power showing up at some frequency because an axion comes along and converts into the photon? So you take this very tiny signal, you need complicated electronics, quiet amplifiers, and so forth. And then you can take a spectrum, and you look at the power spectrum as a function of frequency coming out of the cavity, And if there were an axion, you would expect at some frequency, and the frequency here, of course, would be the mass of the axion, right? At some frequency, there would be an excess in the power that you'd observe. And this feature here would have some line width, as we were discussing yesterday, due to the velocity distribution for the axions. So the axions have some velocity spread on the order of 10 to the minus 3. So if I look at the energy spread, it's going to go like velocity squared. It's going to be on the order of 10 to the minus 6. So this feature here has a width, or a Q factor, if you like, of about 10 to the 6, or a width of delta nu over nu, 10 to the minus 6. And so if one wants to do this experiment, one has to basically park the resonance frequency of the cavity at some particular value, integrate for a while, measure the noise, and see what comes out. And you need to sort of stand at that point at a certain time to get enough statistics so that you can possibly detect a signal above the background. And then you need to move the tuning rod, change the frequency of the cavity by an amount that's basically not much larger than this width, and then repeat this over and over again and kind of scan through a bunch of frequencies. And that's why these experiments can take quite a while to accumulate data over large ranges of axion masses. So the ADMX experiment has this is a schematic. It's a cryogenic experiment done in a helium viewer. So this is a picture of the inside of the copper cavities for the ADMX experiment. So they have this tuning rod, which can be moved around in the cavity, again, so that you want to match the resonance frequency of the electromagnetic modes to the oscillation frequency of the cosmic axion field. Yeah. Oh, you can't hear? Oh. On this particular slide, or I can try to raise the mic too. Is that better? Okay. Well, anyway, so yeah. So I was just saying. So this is the ADMX cavity, and so in this experiment you have this tuning rod inside the cavity that needs to move around, and when it moves around, then we can adjust the frequency of electromagnetic mode inside the cavity that's resonant with the structure from the geometry. And you need to move it so that the oscillation frequency of the axion field, or the mass of the axion, matches the resonance of the cavity, and you kind of scan it as you move that rod inside. Okay, so there's a second generation of the ADMX type experiment, the ADMX HF, or haystack as it's called. This is a smaller cavity, so it's looking for higher frequency or higher mass axions. This is at 5 gigahertz as opposed to hundreds of megahertz where the other experiment was. And it uses quiet amplifiers that are called Josephson parametric amplifiers that are quantum limited amplifiers to improve the noise in the experiments. So there was a nice result recently, just from 2017, where a publication came out where they're now, with the second generation version of this experiment, also able to probe very close to the territory here where one would generically expect, theoretically, the axion coupling to live. And so this is a first demonstration, but it shows that over a narrow range in mass here, they have actually achieved sensitivity that's good enough to start to probe into this region as well. So now there are actually 2 experiments that will be, or will be able to take data to search for the axion at this point. So we can ask, well, what about the sensitivity of these Helioscopes? And so I think we already saw a bit of the derivation for this formula yesterday, so I'm not going to go through that again today. I just wanted to point out some features. So this is the power deposited by axions. And so there's some prefactor here that depends on the property of the axion. There's this coupling constant, which could be 0.9 or 0.3, depending on what axion model you have, KSVZ or DFSZ, for example. This is the dark matter density, fine structure constant, at some energy scale here. There's the properties of the cavity. This is the frequency of the cavity, the magnetic field squared, the volume of the cavity. This is the form factor that tells you about the mode overlap of the cavity, and with the Axion field. Then you have the Q of the cavity, which is an important parameter, as well as some coupling parameter, which describes the efficiency of coupling to your receiver, beta, right? And so in terms of this parameter space plot I showed, we wrote this in terms of this physical coupling in the Lagrangian G, A, gamma, gamma. So that coupling is simply related to this prefactor here, where G, A, gamma, gamma is just this G gamma alpha over pi lambda squared M Axion, where this G gamma is this dimensionless number. And so this is the signal, and so then the experiment is about picking up a signal on top of the background noise, and so the important thing to look at is the signal-to-noise ratio. So this is what we call sigma here. This is the power deposited by axions in the cavity, and then over K times some noise temperature times the square root of the integration time over the axion line width. And so this temperature here, or the signal-to-noise ratio, is what's going to determine how fast you can scan through different frequencies, how long you have to sit at a particular frequency in order to acquire enough signal to determine whether the axion is at that frequency or not. And so this has to do with the physical temperature as well as any noise that the electronics and amplifiers add to the system. And so you can see here, if you want a sensitive experiment, you want to have a low temperature to improve the signal-to-noise ratio. You don't have much control over the axion line width. You can integrate, of course. The longer you integrate, the better your signal-to-noise, but then you pay the price from taking a longer time to scan over different frequencies. And you want to maximize this power, so you want a big volume, you want a high magnetic field, and you want a high Q. And so you can say, well, now let's try to see what the issues are when you try to search for higher frequency axions. So we have these cavity parameters which are able to control the volume, the magnetic field, and to some extent the Q, although we don't always have full control over that. So the volume of the cavity is shrinking as the electromagnetic mode gets smaller. This is generally causing a pretty steep penalty in your sensitivity as you try to couple a cavity to a higher frequency or higher frequency axion. We heard some nice ideas yesterday from Javier about using, for example, the Mad Max experiment to get around some of those limitations. The other issue here is that the Q of the cavity tends to become worse for higher frequencies, and so this additionally hurts you when you try to do a higher frequency experiment. And so, but there are some ideas to get around these limitations. So one of them is the so-called open resonator idea. So there was a prototype experiment at the University of Washington called Orpheus, where basically you have it's essentially rather than an enclosed microwave cavity type structure, it's a Fabry-Perot cavity. Basically, we just have a kind of a one-dimensional set of mirrors here, and then you have these rectangular grids of wires that can be positioned along these rods to sit somewhere along the length of the cavity. And so the idea is you have a higher frequency axion with many oscillations, many mode oscillations that would fit inside the Fabry-Perot cavity, and you could arrange this grid of wires so that the coupling of the magnetic field can actually get, so that the magnetic field profile can actually match very well to the profile inside the cavity. And so basically by having these unmovable arms, one could adjust then the frequencies over which that you'd be searching for. And so the concept here showed a preliminary experiment where their sensitivity is not close to the QCD Axion level, but nevertheless that the technique works at some level, and they project that they could potentially get to the point where they can search for axion masses that are order of tens of micro, or to 100 kind of micro electron volts. And of course, we heard yesterday about a really nice concept for a mirror, a different kind of experiment with where we had dielectric structures inside of a cavity, which could potentially also look for higher frequency axions. At the lower end of the frequency spectrum, we have a few issues. The axion signal is getting weaker. You still need big volumes, and now the magnets are getting expensive. If your cavity size gets larger and larger, you need more and more magnet. Of course, magnets are often the limiting expense in these experiments. So it was pointed out as early as 2010 by Blas Cabrera and Scott Thomas at this Axion workshop that one can think about replacing this microwave cavity structure with a LC resonant circuit type geometry. And so now this basically allows us to avoid having a cavity structure, and rather we're looking more at just we're looking at kind of lumped element circuits rather than cavities. And so for LC resonant circuits, we can try to understand what's going on going back to Axion electrodynamics. So this was worked out by Frank Wilczek in the 80s. Javier also said something about this yesterday with regard to the process for converting to photons, but I want to look at a little different limit now. So this is the Lagrangian E dot B times A. So this kappa here is going to be the same as our G A gamma gamma that I had before. So you can write down the four Maxwell's equations if you add this term to electrodynamics. And in particular, I want to look at the last line. This is where the curl of B. So the terms here with the tilde are the ordinary E and M currents and current and charge density. These terms here are extra due to the axion. So this first piece in particular looks like G A dot times the magnetic field. And so that's going to be the term responsible for producing a signal in these LC resonant circuit experiments. And so if I have an external magnetic field, B naught, then I can basically generate what looks like let's call it a current J axion that's added to any ordinary current here. So J axion is produced by the coupling to the axion, and it goes like the time derivative of the axion field times to B naught times G. So you see it's in the direction, the current's in the direction of the applied external field. Okay, so in an LC circuit, so here's a schematic for a prototype that was in a paper by Sakivi and Sullivan and Tanner in 2014, based on the same concept. So this is basically the cartoon version. So you have a cavity, or so you have a magnet here with a wire loop, and if you apply a magnetic field in the vertical direction here, then from our Axion electrodynamics equation over here, we're going to get some J axion, some current that's going to be along this direction, and now it's going to be time varying with the ADT, right? So the axion field is oscillating at the Compton frequency, right? And so we're going to get some oscillating current in this direction. So if I have the oscillating current, I'm going to produce a real magnetic field, right? This is Maxwell's equations. I'm going to produce a real magnetic field that's curling around the B naught. So I have a magnetic field that's kind of oscillating, that's going around that static magnetic field. And that oscillating magnetic field is then going to change the flux through this pickup loop. So you're going to put a pickup loop inside that cavity, or inside this magnetic field, and that changing flux through the magnetic field is going to create a signal in this magnet for this magnetometer. So basically, you'll produce a current through Lenz's law to oppose the change in flux, and then you can measure with your squid here the signal from that current. And so then that current gives you a signal that's now sensitive to the axion field. And it depends on the inductance and the Q and the volume and so forth. Okay, so using this geometry, they suggest that it's possible to reach down close or at the Axion coupling. This is now this G A gamma gamma again as a function of mass. This is now micro EV and below. So now we're looking at light mass axions, which would be relevant for the type 2 scenario where you have low energy scale inflation. So you have low axion masses here, and with it, depending on how aggressive you are with your magnet, you can now start to potentially probe into the QCD Axion parameter space using this approach. Another very similar experiment, but on a slightly different geometry, was proposed in 2016 by Jesse Thaler and company, where they pointed out that it was potentially useful to use a toroidal geometry here in order to keep a magnetic field kind of enclosed within a volume. And so you have some toroidal structure here with a superconducting shielding around it. And so you have the magnetic field enclosed within the toroid. So the axion current, again, is parallel to the static magnetic field. And so if you have the static magnetic field, then there's a azimuthal component of that, right? And so that azimuthal component will then come out the top and the bottom. It looks like a current loop, basically, right? So you have a magnetic field that comes out of the center of this thing that's oscillating up and down in this direction that can be picked up by a pickup loop where the dotted red line is. There's this gap here. You have this gap in that conductor so that the Meissner effect, the screening current from that Meissner effect can't cancel the real magnetic field that we produced from the axion field. So the axion magnetic field then can be picked up as an oscillating signal in this pickup loop. And so the sensitivity here is, again, on the same kind of graph, able to probe into the QCD axion space for sub-micro EV kind of axions. And there's another experiment that's based on a very similar concept called dark matter radio that's aiming, depending on the size of their detector and field and so forth, to also be able to cut into the QCD Axion parameter space at kind of micro EV and potentially a bit below. Okay, so that's sort of the Helioscopes. Then there's also the so-called Helioscopes. Helioscopes are nice because they don't make any assumptions about the local dark matter density on the Earth. Rather, you have to assume that you know something about what's going on with solar physics. So it's a little bit less model dependent in some way. And then the light shining through walls experiments are independent, of course, of these sort of assumptions, since you're directly trying to convert axions into photons by creating them in the laboratory. But then again, the sensitivities are not so favorable for QCD axion, but rather just looking for axion-like particles. So these are nice. This is nice because you have a lot of good experimental control over your system, but then it does have that sensitivity issue. So the Helioscopes, this is a photo of the cast CERN Axion solar telescope. So basically you point this thing at the sun and you have energetic axions that are produced in the sun, and you're looking for a conversion of the axion to an X-ray. So you have a strong magnetic field here, and we look for that high energetic axion to convert into an X-ray in that background magnetic field. And then there's the proposed future version of cast IAXO, which is this, to give you a sense of scale. Here's a person, so this is a really, I would say, kind of maybe stepping away from the topic of small-scale experiments a bit, but nevertheless, I think it's a very interesting, potentially very useful addition to the search. And then the Axion light particle experiment, basically the idea, or this any light particle, it's called search experiment. So basically here the idea is you're again using this Primakov effect. You have a photon interacting with the backgravity field to produce an axion inside of an optical cavity that's on one side of a wall. And then if you do produce the axion, then the axion can go through the wall and enter another resonant cavity. And in that resonant cavity, there's another enhanced conversion process for the axion to go back into a photon. And so you try to see whether any of the light on this side of the wall makes it over to the other side. This is a concept drawing from their website here if you want to read more about it. So the power converted for this, or the probability rather of conversion is quite small, 10 to the minus 17. Of course, you have a lot of photons you can throw at this thing, but this is still a pretty small number, 10 to the minus 17 for 10 Tesla and 10 meters, assuming around 10 to the minus 10 Joule inverse for G, A gamma gamma. This is all, those are square. And so you pay this price, you pay this twice actually, because first of all, you have to produce the axion, and then you have to convert the axion back, right? So it's a relatively weak process, but it's nice because it's so controllable in the lab. Okay, so back to this plot. So I've shown pretty much the description of all the experiments, most of the experiments on here. At this point, again, looking for this axion to photon coupling. And so back to this plot. So then let's put some of the experiments on here. So the dark matter radio, LC circuit, and abracadabra experiments are filling in some of this area, hoping to fill in this gap where there's no experimental efforts currently or planned. And then in this area here, we have potential for starting to probe into this region with the Orpheus type or Mad Max style of experiments. And then also there are spin-based experiments, Ariadne, which is an experiment we're working on, the Quax experiment, and then Casper, which are based on measuring axion coupling to spin that can also potentially start to fill in this part of the parameter space and lighter mass axions, nano EV and below. Okay, so let me switch then to discussing axions coupling to nuclei. So basically you have the idea is you have so to really understand how this works, I was going to, actually let me use the board for a little bit and kind of explain a bit about how NMR works. So many of the experiments that were that I'll be discussing use nuclear magnetic resonance. And so probably most people in particle physics see NMR maybe in quantum mechanics class and then forget about it and never use it again. So I want to give a quick primer NMR for particle physicists before I continue with the experiments. So, so just a few slides or a few notes on that first. Okay, so if I have just consider a simple quantum mechanical system. So just take a two-level system. Where I have some energy levels, states. There's some energy splitting between these. So we can think about mapping that two-level system onto a spin 1/2, which will be relevant for many of the experiments I'm going to talk about. So if I have a spin 1/2 particle in a magnetic field, And so then the Hamiltonian for a spin 1/2 particle in magnetic field is just mu dot B. Right, this is the magnetic moment. Here's the magnetic field. So we can then label the states here. Spin up and spin down, where there's some energy difference between those that are set by the magnetic field. So the magnetic moment, mu, is proportional to the spin of the particle with some constant gamma. We call this the gyromagnetic ratio. So the spin operator is just, we can think of it as h bar over 2 times the Pauli matrix. And the gyromagnetic ratio, we can write in terms of this Bohr magneton over h bar times some g factor. So for electron spin, the g factor is nearly 2. Or, for example, if I have a nuclear spin, I would relate this to the nuclear magneton. So when we talk about quarks, we'll be concerned with electron spin. When we talk about Casper or Ariadne, then the nuclear spin is the relevant thing. So to give you some examples, so for helium-3, this is a spin 1/2 nucleus. Then this gyromagnetic ratio is about 32, minus 32.4 megahertz per Tesla. And for the electron spin, gamma is going to be 2.8 gigahertz per Tesla, so quite a bit larger. And that's assuming, again, here this is a G factor of 2. So the frequency omega naught then is just going to be given by gamma times the applied field. And so then depending on the field that you apply to the system, you can control the resonance frequency between the two states. So I can, let's consider, okay, so the Hamiltonian then I can write in terms of these as sigma dot B. And let's consider a constant magnetic field along the z direction. So then H is going to be minus h bar over 2 omega naught sigma z, the Pauli matrix. And the eigenstates are spin up with eigenvalue minus h bar omega naught over 2, or spin down, opposing the field with h bar omega naught over 2. And the generic state can be, of course, represented in that basis where I have psi is some linear combination of up and down, where I can normalize those coefficients, where each one of these is some complex number. Okay, and so I can prepare, suppose I prepare an initial state that's some superposition of these up and down. And then I can ask what happens to the time evolution of that state in the magnetic field. So this, of course, is governed by the Schrodinger equation. Where there's some energy in this exponential that's governing the relative phase acquired by the spin up and spin down part, right? And so this time evolution, when we have this relative phase changing here with time between the two components, can be looked at as a geometric precession that's known as Larmor precession of the spin. And this is going to be important for the understanding the way these Axion experiments work. So we have a time-dependent phase shift between spin up and spin down components of the state. So if I were to measure, for example, starting with that state, if I were to measure the spin along the x direction, so then I would need to know the eigenstates of sigma x, the Pauli matrix. So this is 1 over root 2, 1, 1, or 1 over root 2, 1 minus 1. Then I could compute, for example, if I call this one the eigenstate x plus for pointing along the x direction, I can compute the probability of finding eigenvalue plus h bar over 2 by taking this inner product squared, and I'm not going to do the algebra, you get cosine omega naught t over 2. If I look at the probability of measuring the spin along z, then of course I get 1/2, and this is unchanged. We're measuring spin up along the z-axis. And so geometrically, this oscillating situation can be mapped onto a spin vector that's rotating in the plane at frequency omega naught. And so I can see that by computing the expectation values. So if I compute psi expectation of sz, I'll get 0. So I'm somewhere in the equator between up and down. If I measure expectation of Sx, you can work out this is going to be h bar over 2 cosine phi plus omega naught t. And for Sy, h bar over 2 sine. So basically this spin is precessing perpendicular to the direction of the magnetic field. And we can make a nice geometric picture of that, like the shown in the sphere up there. So we have these coefficients, alpha and beta, that are normalized to 1. So we basically have 3 real numbers to specify the state. So we can write these as the coordinates on a sphere. Finding some angles theta and phi. Right, and so if I have some state vector, I have some polar angle as well as some azimuthal angle. I can write the alpha and beta in the following way in terms of the angles. So this is cosine theta over 2 up plus sine theta over 2 e to the I phi down. So if phi is 0, then it's going to point along x. If I have theta equal to pi over 2, or phi equals pi, for example, it would point along minus x. So the general state is some vector that points somewhere on this unit sphere, right? And so if I were to measure the spin along the n direction, which is along wherever that spin is, then this would be an eigenstate of sigma n, if you like, the Pauli matrix pointing in the nth direction. So let's call that the n direction. So then the general, I can ask what happens to that state under time evolution. So solving the Schrodinger equation, I'm going to redefine the energy so that the lower energy is 0 and the other one is just h bar omega to make life simple. So we pick up this relative phase here, omega t. So here I'm setting the low energy to 0 to get rid of that overall phase. And so then theta of t is constant, and phi of t is phi plus omega naught t. So the angle, if this is in the n direction, the angle between n and b is a constant. And n of t is going to rotate around z at the angular velocity omega naught, which is proportional to b. So if I prepare a spin in a state that's perpendicular to the field, it precesses around the field, and this Larmor precession is going to be the signal that the Axion experiments I'm talking about are going to pick up. They're going to pick up that precessing spin, or some of them anyway, are going to pick up that precessing spin. Okay, so there's one more piece of physics related to NMR I need to tell you about to really understand how the Axion experiments work. That is the idea of Rabi oscillations, which I'm sure everyone has heard of from quantum mechanics, but maybe doesn't remember since it's been a while. Okay, so now I want to ask what happens. So imagine I have my uniform magnetic field in the z direction. And let's add a transverse magnetic field. Oscillating magnetic field. Let's call it B1. Say it's in the x direction with some time dependence. And so what I want you to have in mind here, what we have in mind here is we're going to connect this to the oscillating Axion field. But for now, it's an ordinary magnetic field in the lab, perpendicular to the static field in the z direction. So I can write the Hamiltonian out. Including the time-dependent part and the regular part, where now I've defined frequencies omega naught, this is gamma b naught, and omega 1 is gamma b1. Generally speaking, and certainly for the case of the Axion experiments, the b1 field is usually small compared to the b naught, so we're thinking about this as a small time-dependent perturbation in the transverse direction. And let's assume the initial state is in the ground state. So on the sphere, the initial state, the state vector is pointing up at the North Pole in the ground state. And I'm going to assume that the frequency omega is close to omega naught, so that it's nearly resonant. The frequency of this oscillation is nearly resonant with the energy splitting between spin up and spin down. So we can, this is a 2x2 matrix. You can diagonalize it, you can solve it exactly. I'm going to save you some of the work for that. I'll just show you the result. But what we can do is basically think about this in a rotating frame. Since we know we have this Larmor precession generally going on at the frequency omega naught, we can make the problem simple by going to a rotating frame at omega naught. You can solve the Schrodinger equation, which I don't have time to go through the steps in order to, I don't want to bore you. So the probability of making a transition, so this radiation, this can be thought of as like a magnetic radiation. It can give me some probability of making the spin flip from state 1 to state 2. I can calculate that probability, omega 1 squared over gamma squared sine squared omega t over 2, where this big omega is the square root of the sum of the difference between the frequency of the applied field and the energy splitting frequency squared plus omega 1 squared. And so if I plot that probability, from going from state 1 to 2 as a function of time. This is 1 and this is 0. We have these oscillations. So this is if omega is equal to omega naught, then the probability goes all the way to 1. So if omega equals omega naught, this term vanishes, and this prefactor here is 1. So my probability goes like sine squared, which goes to 1 at some particular time. And these are called Rabi oscillations. And then if omega is not equal to omega naught, from off the resonance, I pick up a contribution from here. This term is in the denominator. It's bigger than omega 1 squared, so it decreases the probability. So off resonance, I have less probability of making the transition. And also the frequency here that this occurs is increasing according to this term here. So if I'm off resonance, then the probability looks something like that. Okay, so we can think about this back in the language of our sphere here. It's a nice geometrical way to understand what's going on. And so if I go back to the block sphere, as it's called, so the state vector for the magnetization of the particle, I can call it m, that's the vector pointing on that sphere. And so the evolution of that vector follows an equation that's identical to the torque and a classical spin in a magnetic field. And in this rotating frame, rotating at the frequency omega naught, I can write this equation the following way. I'm going to switch this to W. So this is the rotating frame. Then the torque vector W is going to be, in our case, omega 1 along the x direction plus omega minus omega naught. I'll call delta along the z direction in the rotating frame. And so we're basically just mapping the dynamics of the Schrodinger equation onto this evolution of these three numbers, which are the components of this vector that match this classical evolution of this torque on a classical spin. And so since we have this equation, then we can see that m dot m is 0. So the amplitude is constant. So the vector always is a unit vector on the sphere. And the m dot w is also 0, since we have the cross product. So m w cosine theta is constant. So the block vector m moves along a cone with theta equals constant. And it precesses about W. So if I have my sphere here, say this was the x direction, then my block vector would precess around W. If this frequency difference delta is 0, then the torque vector points strictly along x, and the block vector will precess around this direction. If the this delta is not 0, then I could have some torque vector pointing somewhere else in the xz plane. In that case, then I would process, the block vector processes around the torque vector in this way. And so this is directly mapped onto this problem here. So in the case where the probability goes from 0 to 1, the vector is processing around the x direction. It goes from pointing all the way up to all the way down. When it's all the way down, it corresponds to the point on the top with the probability of 1 of finding it in the other state. And this oscillates back and forth. If you have some detuning, then you still have an oscillation of the block vector around the torque, but it never deviates very far from the initial position. And so then the probability is never very high for getting to the excited state. So this is just a mathematical tool for basically visualizing the dynamics of the spin, which is very helpful to understand the experiment. And so this is now going on in the rotating frame. In the lab frame, where we actually do measurements in the lab frame, what happens is, let's just look at this first case here. You have the spin pointing up. And this block vector is going to start tipping down away from the z-axis. But at the same time, we have the Larmor precession now. We're putting the Larmor precession back in. And so what we'll see is that the block vector actually will start to spiral like that as the interaction happens. So when we apply a magnetic field transverse to the static field at some frequency at resonance, then in real space, the magnetization vector is going to start precessing and tipping away from the z-axis and then picking up a transverse component that's oscillating. And that's going to be the signal for our experiments where the Axion field is going to play the role of the transverse field, and then that's going to cause the magnetization of our NMR sample to oscillate, and we're going to try to pick up and measure the Larmor precession of that system with the sensor. And so far, this is basically, this block sphere picture is just mapping the coherent evolution from the Schrodinger equation onto a different mathematical structure. But the block sphere is actually also useful for going beyond that, where I can add relaxation terms. And the relaxation terms I just want to say a bit about, because they'll also be important for understanding the limitation of the experiment. So in these block equations here, I can also, if I write down all the components, I can add damping terms. So the T1, this is the longitudinal decay. Right, so with coherent evolution, I could prepare the system in the ground state, put it in the excited state, and just leave it there, and it would just stay there. In reality, there's some decay process where the high energy state is going to decay to the lower energy state with some decay time constant that's called the T1 longitudinal decay. There's also the transverse decay, which will be limited in the experiment sensitivity. Transverse decay is basically describing the lack or the destruction of the coherence in a coherent superposition between the two states. So I have basically looking at the coherence in the transverse direction and the XY directions of the block sphere. And often there can be mechanisms that contribute to one type of decay but not the other for different experimental considerations. Okay, so here's a nicer drawn version of the sphere here, and so that's a picture I want you to keep in mind when we talk about the upcoming NMR-based experiments. So I just want to maybe do a couple more slides, and then maybe we'll break for the next lecture. So this is now kind of a cartoon picture of this NMR, essentially. So what we have here is an ensemble of spins. They're oriented along some external magnetic field. If you have a transverse magnetic field that's oscillating, if the frequency of the oscillation of the magnetic field that's transverse coincides with this energy difference from the Larmor frequency, then we get a spin flip. Okay, and so that's the principle on which the Casper experiment is going to operate. This was proposed back in 2014. Basically, what you have here is an external field and a set of spins, and our transverse field is going to be produced either by the Axion wind or by an effective electric field. And the Larmor frequency is going to be tuned to match to the Axion mass to get a resonant enhancement, and then a squid is going to be used to measure the transverse magnetization. So I think I'm going to maybe stop here for questions and continue with this at the next lecture.